Space has always been the ultimate enigma, a vast, silent frontier where the rules we know seem to twist, bend, and sometimes shatter entirely. Think about it. We send probes to distant worlds, build telescopes that peer back in time, and yet the universe keeps throwing curveballs that leave even the brightest scientists scratching their heads. What if I told you there are moments in the cosmos so bizarre, so utterly inexplicable, that they defy the very laws of physics we've staked our understanding on? That's not science fiction, it's real, and today we're diving into 30 of these mind-bending phenomena that will make you question everything you thought you knew about the universe. Picture this, a black hole spinning so fast it warps space-time like a cosmic whirlpool, or a galaxy moving at speeds that shouldn't be possible without some invisible force yanking it forward. These aren't plot twists from a sci-fi movie, they're real mysteries etched into the fabric of space itself, waiting to be unraveled. And here's the kicker, every time we think we've got the universe figured out, it throws another puzzle our way, as if it's testing the limits of human curiosity. That's the beauty of space, it doesn't play by our rules, it writes its own. So buckle up, because we're about to embark on a journey through the cosmos's greatest defiance acts. From stars that vanish without a trace to particles that seem to communicate faster than light, each of these 30 phenomena will leave you awestruck. Whether you're a seasoned space enthusiast or just someone who loves a good mystery, this is your front row seat to the universe's most baffling performances. By the end, you'll see why space isn't just the final frontier. It's the ultimate rebel rewriting the rules right before our eyes, ready to have your mind blown. Let's dive in. The Pioneer Anomaly is one of those cosmic head-scratchers that left scientists utterly baffled for decades. Picture this, in the 1970s, NASA launched the Pioneer 10 and Pioneer 11 spacecraft on a grand tour of the outer solar system. These robotic explorers performed flawlessly until something strange happened. As they ventured farther from Earth, tracking data revealed they were slowing down ever so slightly, as if an invisible hand was tugging them backward. According to Newton's laws of motion, once these probes escaped Earth's gravity, they should have coasted through space at a constant speed, but that's not what happened. Instead, they experienced a tiny but persistent deceleration, just about 10 billion times weaker than Earth's gravity, but enough to throw off their trajectories. At first, scientists thought it might be a simple calibration error or a glitch in the data. But as years passed and the anomaly persisted, the hunt for answers grew more urgent. Was it fuel leaking from the probes? Nope, calculations ruled that out. Could it be the faint push of radiation from the spacecraft's own power sources, gently nudging them off course? That was a leading theory for a while, but even meticulous modeling of heat radiating from the probes couldn't fully explain the discrepancy. Then came the wilder possibilities. Maybe it was dark matter's gravitational whisper, or even a flaw in our understanding of gravity itself. Some researchers even speculated about entirely new physics, suggesting Einstein's relativity might need tweaking at cosmic scales. After years of analysis, the most plausible explanation turned out to be surprisingly mundane, though no less fascinating. Detailed reconstructions of the spacecraft's heat signatures revealed that thermal radiation, emitted unevenly from their aging power systems, was acting like a minuscule thruster, slowing them down in a way engineers hadn't anticipated. It was a masterclass in how even the tiniest overlooked detail can unravel centuries of scientific certainty. Yet the Pioneer Anomaly remains a cautionary tale, a reminder that space, even in our own cosmic backyard, is full of surprises waiting to upend what we think we know. If the Pioneer Anomaly made scientists question their understanding of deep space physics, wait until you hear about the Flyby Anomaly, a glitch in gravity's playbook that happens shockingly close to home. When spacecraft like Galileo and Rosetta swung past Earth to get a gravitational speed boost for their long journeys, something bizarre occurred. Instead of following Newton's precise equations, these probes either gained or lost speed in ways no one could predict. Imagine throwing a ball and watching it suddenly zip faster midair. That's essentially what happened, except with billion-dollar machines hurtling through space at thousands of miles per hour. At first, the discrepancies seemed small. During Galileo's Earth flyby in 1990, it accelerated an extra 3.9 millimeters per second beyond calculations. Rosetta's flyby in 2005, a 1.8 millimeter per second hiccup. Tiny numbers, sure, but in the hyper-precise world of orbital mechanics, even a whisper of unexplained force raises alarms. Scientists scrambled to check their math. Had they misestimated Earth's gravity? Maybe atmospheric drag played a role? Nope. Every conventional explanation fell short. That's when the theories got wild. Some suggested frame dragging Einstein's idea that a rotating planet like Earth literally twists space-time around it like honey swirling around a spoon. Could this subtle warping nudge spacecraft off course? Others pointed to dark matter, proposing invisible clumps near Earth might be tugging on probes. Then there's the possibility that our maps of Earth's gravity field are incomplete, hidden mass variations deep in the planet's crust acting like unseen speed bumps or accelerators. But here's the real kicker. These anomalies only show up during flybys, never in other scenarios. It's as if Earth's gravity has a secret setting that only activates when spacecraft zip by. To this day, no single theory fully cracks the code. The Flyby Anomaly remains a cosmic wink, a reminder that even our home planet, the place we know best, still holds physics-defying surprises in its gravitational embrace. Just when we thought we had the universe's expansion figured out, astronomers stumbled upon something that flipped the script entirely: dark energy. Picture the cosmos like a loaf of raisin bread baking in the oven with galaxies as the raisins. For decades, scientists assumed gravity would slow the bread's expansion, pulling those raisins closer together over time. But in the late 1990s, two separate teams studying distant supernova made a jaw-dropping discovery. The universe wasn't just expanding, it was accelerating, as if some invisible force had cranked up the oven's heat. Those far-off stellar explosions, known as Type 1, a supernova, appeared fainter than expected, meaning they were farther away than standard models predicted. The only explanation: space itself was stretching faster and faster, defying gravity's relentless pull. This wasn't just a minor tweak to cosmic theory, it was a full-blown revolution. Einstein's equations had once included a fudge factor called the cosmological constant, which he later abandoned, calling it his greatest blunder. Now it was back with a vengeance, rebranded as dark energy, an enigmatic pressure permeating the vacuum of space and pushing galaxies apart. The numbers are staggering. Dark energy makes up roughly 68% of the universe's total energy budget, while ordinary matter, the stuff of stars, planets, and us, accounts for less than 5%. Yet despite its dominance, we have no idea what dark energy actually is. Is it a property of space itself, or does it hint at entirely new physics beyond Einstein's framework? The implications are mind-bending. If this acceleration continues, distant galaxies will eventually vanish beyond our cosmic horizon, their light never reaching us again. The universe could end not with a crunch, but with a cold, silent fade-out, a fate far lonelier than anyone imagined. And here's the real kicker: dark energy's strength seems perfectly fine-tuned to allow galaxies, stars, and life to form. Change its value even slightly, and the universe either rips itself apart too soon or collapses before complexity can emerge. It's as if the cosmos is balanced on a razor's edge, and we're left wondering why. For now, dark energy remains one of physics' most profound puzzles, a reminder that the universe still holds the upper hand in this grand cosmic game. In the quiet hum of the universe's radio static, one burst of sound stood out so sharply that an astronomer scrawled, "Wow," in the margins of the data printout, a name that would stick forever. On August 15, 1977, Ohio State University's Big Ear radio telescope picked up a signal so unusual it defied all expectations. For 72 seconds, a narrowband radio wave blazed at a frequency of 1,420 MHz, the exact wavelength hydrogen absorbs and emits energy, a logical choice for any civilization trying to announce its presence. The signal was 30 times louder than the cosmic background noise, vanishing as abruptly as it appeared, never to be heard again. Theories about its origin range from the plausible to the extraordinary. At first, some dismissed it as earthly interference, maybe a passing airplane or a wayward satellite. But the signal's frequency was locked in a water hole, a radio band so quiet that human-made transmissions are banned to avoid cluttering the search for extraterrestrial intelligence. Others suggested a natural cosmic source, like a comet's hydrogen cloud reflecting sunlight. Yet when researchers revisited the area in 2016, tracking the path of two comets that hadn't been catalogued in 1977, no similar signal emerged. The comets were silent. Then there's the tantalizing possibility: was it aliens? The signal's intensity and frequency fit the profile of an intentional broadcast, a cosmic hello beamed across the stars. But if so, why only once? A civilization advanced enough to send such a signal would presumably repeat it unless it was a fleeting burst, like a lighthouse beam sweeping past Earth just long enough to catch our attention. Skeptics counter that the universe is vast and chaotic, capable of producing rare, unexplained phenomena without invoking little green men. Decades later, the wow signal remains a mystery, a one-time enigma that refuses to surrender its secrets. No telescope has ever caught anything like it again, despite countless scans of the same patch of sky near the constellation Sagittarius. It's the ultimate cosmic teaser, a whisper from the void that challenges our certainty about whether we're alone. Whether it was a natural fluke or something more profound, one thing's clear: for those 72 seconds, the universe had our full, undivided attention. Fast radio bursts are like the universe's Morse code, blindingly intense, impossibly brief, and utterly unpredictable. These cosmic flashes pack more energy than our sun emits in days into mere milliseconds, vanishing before we can even pinpoint their origin. The first one was discovered in 2007, buried in decades-old radio telescope data, and since then, hundreds more have been detected, each one a fleeting shout from the depths of space. What makes them truly baffling is their sheer power. Some release as much energy as 500 million suns, all in the time it takes to blink, and then they're gone, leaving astronomers scrambling to decode their secrets. Then there's the twist: not all fast radio bursts are one-hit wonders. In 2016, scientists found one that repeats, firing off signals in irregular patterns like a cosmic heartbeat. This wasn't just a random explosion, it was something with staying power, a source that could erupt again and again. The leading suspect, magnetars, neutron stars with magnetic fields so intense they could strip atoms apart from thousands of miles away. When these cosmic powerhouses quake or flare, they might unleash bursts of radio waves like celestial fireworks, but even that theory doesn't explain everything. Some repeating bursts arrive with a telltale frequency, suggesting they're traveling through turbulent clouds of plasma, while others are eerily clean, as if their journey through space was smooth sailing. Here's where it gets weirder. A handful of these bursts seem to carry a peculiar fingerprint, a cyclical pattern, flaring up every few months before going silent again. It's as if whatever's producing them operates on a cosmic timer, ticking away in the void. Could it be a neutron star wobbling like a spinning top, its magnetic poles periodically aligning with Earth? Or something far more exotic, like the collapse of microscopic black holes predicted by string theory? Even the locations defy expectations. Some bursts trace back to distant galaxies, but one recently erupted inside our own Milky Way, proving these aren't just far-off anomalies, they're happening in our cosmic backyard. The real challenge is catching them in the act. Fast radio bursts are so brief that by the time a telescope swings toward their origin, they've already faded. It's like trying to photograph lightning with a camera that takes minutes to snap a picture. New projects like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are racing to change that, scanning huge swaths of sky in real time to catch these radio ghosts mid-flash. Every new detection peels back another layer of the mystery, but the central question remains: what cosmic phenomenon can unleash such titanic energy over and over without leaving a trace? Until we find the source, fast radio bursts stand as one of space's most electrifying enigmas, proof that the universe still has a few tricks up its sleeve. When astronomers first spotted the light from a star called KIC 8462852 flickering like a faulty street lamp, they knew they were witnessing something extraordinary. Nicknamed Tabby's star after the scientist Tabitha Boyajian who led its discovery, this distant sun behaves like nothing else in the cosmos. Instead of the predictable, gentle dimming caused by orbiting planets, its light drops by up to 22% at random intervals, sometimes for days, other times for years, as if something massive and irregular is blocking its glow. The patterns defied every textbook explanation, sparking a firestorm of speculation. Could this be evidence of alien engineering on a scale we can barely fathom? The most tantalizing and controversial theory suggested a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harness a star's energy. Imagine a vast network of solar panels encircling Tabby's star, each one drifting in and out of view as they orbit, causing those bizarre dips in brightness. It was a concept ripped straight from science fiction, yet for a brief moment it seemed plausible. After all, natural explanations fell short: planets. Even a Jupiter-sized world would only dim the star by about 1%. A dusty debris field from a catastrophic planetary collision. The star's infrared signature didn't match the telltale warmth of fresh cosmic wreckage. Then came the twist. Detailed observations revealed the dimming wasn't uniform. Blue light was being blocked more than red, a clue that pointed not to solid megastructures, but to something far messier: dust. Microscopic particles, finer than smoke, could scatter shorter wavelengths of light while letting longer red waves pass through. This didn't just debunk the alien hypothesis, it deepened the mystery. Where was all this dust coming from? Some researchers proposed a family of comets shattered by a close encounter with the star, their icy fragments vaporizing into vast, uneven clouds. Others wondered if Tabby's star was devouring a moon or even an entire planet, its gravity tearing the doomed world into a swirling, opaque haze. Yet even these scenarios struggled to explain the star's centuries-long fade. Historical data from 19th century photographic plates showed Tabby's star has been steadily darkening by around 10% per century, a slow-motion dimming no known stellar phenomenon can fully account for. Is it cloaking itself in a shroud of its own making, or are we witnessing a cosmic phase never before documented? The truth is, Tabby's star isn't just challenging our ideas about alien life, it's exposing gaps in our understanding of how stars age. Every new observation peels back another layer, revealing not just one anomaly but a nesting doll of puzzles. Whether it's a celestial demolition derby or something even stranger, one thing's clear: the universe has a flair for drama, and Tabby's star is its most enigmatic performer. Stephen Hawking once dropped a bombshell that shook physics to its core: black holes, those cosmic vacuum cleaners, might be erasing information from the universe. That's not just a sci-fi plot twist, it's a direct violation of one of quantum mechanics' sacred rules. Information can never be truly destroyed. Imagine shredding a document and tossing it into a fire, only to realize every single atom of ash still holds the blueprint to reconstruct it. That's how the quantum universe works, except according to Hawking, black holes break the rulebook. When matter falls in, its information seemingly vanishes forever, lost behind the event horizon's inescapable grip. This clash between gravity and quantum theory became known as the black hole information paradox, and for decades it was physics' most glaring unsolved mystery. But here's where things get wild. Hawking himself later backtracked, suggesting information might not be lost after all. It could leak back out via Hawking radiation, the faint glow black holes emit as they evaporate. The catch: that radiation looks totally random, like static on a broken TV. If information is somehow encoded in that noise, it's scrambled beyond recognition. So the puzzle shifted. How does data escape without leaving a trace? Enter the firewall hypothesis, a radical idea proposing the event horizon isn't the calm boundary we thought. It's a searing wall of energy that fries anything crossing it. Picture jumping into what you thought was a pool, only to hit a sheet of flames instead. This firewall would annihilate an infalling astronaut while preserving information for the outside universe, but it comes with a cost, rewriting Einstein's smooth space-time like a glitch in reality's code. Then there's the holographic principle, a mind-bending workaround that reimagines our entire universe as a cosmic projection. Think of a black hole's event horizon like a two-dimensional DVD surface storing all the information about the three-dimensional objects inside it. When matter falls in, its data isn't destroyed, it's smeared across the horizon's surface, encoded in tiny Planck-scale pixels. Later, as Hawking radiation escapes, it carries that imprinted data like a cosmic backup drive. It's a staggering idea. Everything we think of as three-dimensional reality might just be a hologram, with black holes acting as the ultimate data processors. Yet even these theories leave gaps. If information escapes via holograms or firewalls, what really happens to an astronaut crossing the horizon? Do they burn up or pass through unharmed while a shadow version gets scrambled into radiation? The math suggests both scenarios could be true simultaneously, a quantum superposition of gruesome and graceful endings. It's as if the universe itself can't decide, leaving us with a paradox that's both infuriating and exhilarating. Every proposed solution peels back another layer of the cosmos's weirdness, proving that when it comes to black holes, even the laws of physics seem to bend under their weight. One thing's certain: until we crack this puzzle, black holes will keep taunting us with their impossible contradictions, dangling the secrets of quantum gravity just out of reach. Einstein called it spooky action at a distance, a phenomenon so bizarre it made even the greatest scientific minds uneasy. Quantum entanglement, the strange cosmic thread binding particles across the void, defies everything we know about how the universe should work. Picture two electrons born from the same atomic event, spinning in perfect sync millions of light-years apart. Flip one spin to up, and its twin instantly flips to down, no matter how vast the separation. No signal travels between them, no hidden wires connect them. They just know, as if space and time don't apply. This isn't theoretical, it's been proven in labs repeatedly, smashing Einstein's belief that nothing could exceed light speed. China's Misha satellite took this cosmic weirdness to new heights, literally. In 2017, it fired entangled photons from orbit to ground stations 700 miles apart, shattering distance records. Here's the kicker: when researchers measured one photon's state, its partner, still hurtling through the atmosphere, snapped into a mirrored state faster than light could have carried the message. Locality, the rule that objects need time to influence each other across space, gone. The universe appeared to be cheating its own speed limit. But before you dream of real-life Ansibles or Star Trek subspace comms, there's a catch. Entanglement can't send information faster than light. While the particles coordinate instantly, their states are random until measured like synchronized dice that always land matching numbers, but you can't pick which numbers show up. It's cosmic synchronization without control. Yet this very limitation might unlock unbreakable encryption. Quantum keys built on entangled pairs could create communication channels where eavesdropping is mathematically impossible. Any snooping would disrupt the delicate quantum link, alerting users immediately. The implications ripple deeper. Some theories suggest entanglement might weave space-time itself together, with every particle's quantum thread stitching the fabric of reality. Others propose it's evidence of higher dimensions where distance is an illusion. And then there's the wild card: what if we're missing something fundamental? Could spooky action hint at a layer of physics where cause and effect operate outside time as we know it? For now, entanglement remains both a tool and a riddle, a reminder that the universe's deepest laws might be far stranger than fiction. The moon has always been Earth's silent companion, a cratered world we thought we understood until scientists cracked open its rocks and found a story that shouldn't exist. Lunar samples brought back by Apollo astronauts held a jaw-dropping secret. Tiny mineral grains locked inside them were magnetized, as if frozen in time under the influence of a powerful magnetic field. But here's the problem. The moon's core is minuscule, just 1 to 2% of its mass, far too small to generate the kind of planetary dynamo that powers Earth's magnetic shield. So how could this airless, geologically stagnant world once have hosted a magnetic field strong enough to leave its mark on ancient rocks? One leading theory points to a cosmic slingshot effect. Early in its history, the moon was much closer to Earth, and our planet's gravity may have stirred its molten core like a spoon in a cup of coffee. This mechanical pumping could have jump-started a temporary dynamo, generating a magnetic field for a few 100 million years before the moon drifted away and its core cooled. But there's a snag. Computer simulations show this process would have produced a field far weaker than what the lunar rocks recorded, some of which suggest a field nearly as strong as Earth's is today. That's like expecting a flashlight to outshine a stadium floodlight. Then there's the impact hypothesis. The moon's violent infancy, bombarded by asteroids the size of mountains, might have triggered massive magma oceans. As these molten seas sloshed and crystallized, the movement of electrically conductive material could have generated short-lived magnetic surges. Think of it as a geological adrenaline rush, a brief, chaotic burst of magnetism fueled by celestial collisions. But even this can't fully explain the duration of the moon's magnetic activity, which some evidence suggests persisted for over 1 billion years. Impacts are fleeting. Magnetism shouldn't linger like a ghost in the rocks. The plot thickens with the precession theory. Imagine the moon's solid outer shell wobbling like a spinning top, grinding against a still liquid core beneath. This friction could have generated heat and motion, sustaining a dynamo long after conventional models say it should have died. It's an elegant idea, but critics argue the math doesn't quite add up. The forces involved might not have been enough to keep the magnetic engine running for the ages recorded in the rocks. What if the answer lies in chemistry? Recent studies suggest the moon's core might have been rich in sulfur, lowering its melting point and allowing it to stay liquid and active far longer than expected. Sulfur's presence could have altered convection patterns, creating a dynamo that flickered on and off like a faulty light switch. Yet even this leaves gaps. Why do some rocks show signs of a stable field, while others hint at erratic bursts? The moon's magnetic mystery isn't just academic, it's a window into how small rocky worlds evolve. If such a tiny body could sustain a robust field, it upends our assumptions about what makes a planet habitable. Maybe magnetic shields aren't exclusive to giants like Earth. Maybe they're more common in the cosmos than we thought. But until we solve the riddle of those magnetized grains, the moon will keep its secrets close, a silent testament to the universe's knack for defying expectations. One thing's certain, our closest neighbor still has chapters of its story left to tell. When the Pan-STARRS telescope in Hawaii spotted a faint dot streaking across the sky in October 2017, astronomers assumed it was just another space rock until they crunched the numbers. This visitor, dubbed Oumuamua Hawaiian for Scout, was moving fast, too fast to be bound by the sun's gravity. The realization hit like a lightning bolt. We'd just intercepted our first confirmed interstellar object, a wanderer from another star system. But the closer scientists looked, the weirder Oumuamua became. First, there was its shape. Most asteroids and comets are lumpy potatoes or rugged spheres, but Oumuamua was flat like a cosmic pancake tumbling end over end. Then came the real shocker. It was accelerating, not just coasting on momentum, but speeding up as it left the solar system, as if pushed by an unseen force. Comets often behave this way when sunlight vaporizes their ices, creating a jet of gas that acts like a natural thruster. But Oumuamua showed no visible tail, no coma of dust and gas, just pure, baffling motion defying gravity's pull. Theories exploded. Could it be a hydrogen iceberg sublimating invisibly in sunlight? Unlikely. Interstellar space would have long since stripped such a fragile object bare. Maybe it was a shard of a shattered planet, sheared off by some cataclysmic collision and sent careening across the galaxy. Or cue the headlines, was it alien technology? Harvard astrophysicist Avi Loeb famously suggested Oumuamua might be a light sail, an artificial structure designed to catch stellar winds like a boat's sail catches breeze. After all, its acceleration matched the profile of something thin and pushed by radiation pressure. Skeptics fired back. If Oumuamua were a light sail, why no radio signals? Why no visible signs of construction? The lack of outgassing could just mean it was an exotic type of comet with ultra-clean ices, leaving no dusty trail. Or perhaps its acceleration came from a more mundane source, tiny bursts of gas erupting from hidden cracks, too faint for telescopes to spot. Then there's the lingering question of its pancake geometry. Was it a flattened disk from some ancient cosmic collision, or a needle-like object we happened to catch edge on without clearer images? It was already too far away by the time we noticed it. We're left guessing. One thing's certain, Oumuamua didn't play by the rules. It vanished as mysteriously as it arrived, leaving behind a trail of shattered assumptions and a humbling reminder. The universe doesn't need aliens to surprise us. It's plenty weird on its own. The Hubble tension is like two detectives arriving at the same crime scene, but coming up with wildly different stories about what happened. Here's the mystery. When scientists measure how fast the universe is expanding today by studying nearby galaxies, they get one number. But when they look deep into space and thus far back in time using relics like the cosmic microwave background, they get another. These two methods, both ironclad in their own right, disagree by about 9%. That might not sound like much, but in the high-stakes world of cosmology, it's enough to trigger a full-blown crisis. Let's break it down. The local method relies on pulsating stars called Cepheid variables and cataclysmic supernova known as Type 1a. These cosmic yardsticks let astronomers gauge distances to nearby galaxies with astonishing precision, like counting the ticks of a universal metronome. Plug those measurements into Hubble's law, and you get an expansion rate around 73 kilometers per second per megaparsec. But when scientists peer back to the universe's infancy, analyzing the afterglow of the Big Bang with instruments like the Planck satellite, the math suggests a slower pace, roughly 67. It's as if the universe started jogging at one speed and then suddenly sprinted, defying all expectations. This discrepancy isn't just a rounding error. It's a fundamental rift that could mean our understanding of physics is missing a crucial piece. Some theorists point fingers at dark energy, the mysterious force accelerating cosmic expansion. Could its strength be changing over time, like a dial being tweaked behind the scenes? Others wonder if dark matter, the invisible scaffolding holding galaxies together, has properties we've completely overlooked. Perhaps it interacts with itself in ways we never predicted, subtly altering the universe's growth rate. Then there's the nuclear option. Maybe we're dealing with entirely new physics. Some daring proposals suggest modifications to Einstein's gravity or the existence of extra, hidden dimensions warping space-time in ways we can't yet detect. Others float the idea of early dark energy, a fleeting force that existed for a cosmic instant after the Big Bang, imprinting its fingerprint on the ancient light we see today. The stakes couldn't be higher. If the Hubble tension holds, it implies that somewhere in our cosmic equations there's a hidden variable, a shadowy player reshaping the universe in ways we're only beginning to glimpse. Future telescopes like the James Webb Space Telescope or the Vera C. Rubin Observatory may finally crack the case by sharpening our measurements of distant galaxies and ancient light. Until then, this cosmic speed disagreement stands as one of the most tantalizing puzzles in modern science, a reminder that even our best models of the universe are still works in progress, waiting for the next breakthrough to set them straight. In 2011, a physics experiment in Italy sent shockwaves through the scientific community with a claim so bold it seemed to rip a hole in Einstein's theory of relativity. The OPERA collaboration, a team studying elusive particles called neutrinos, announced their detectors had captured something impossible. These ghostly particles were arriving 60 nanoseconds faster than light could travel the same distance. To put that in perspective, it's like a runner crossing a marathon finish line a fraction of a second before the starting gun fired. If true, it meant neutrinos were breaking the cosmic speed limit, defying a century of physics dogma. The implications were staggering. Einstein's special relativity hinges on the idea that nothing can outpace light. It's the universe's ultimate traffic cop, enforcing causality and keeping time flowing smoothly. If neutrinos could cheat this rule, it would upend everything from how we understand black holes to the very fabric of space-time. The scientific world erupted. Some theorists scrambled to propose wild explanations. Maybe neutrinos were taking shortcuts through extra dimensions, or perhaps relativity had loopholes no one had spotted. Others smelled a rat. 60 nanoseconds is an eye blink in human terms, but in particle physics, where timing is measured with atomic clock precision, even a tiny error could skew results. Then came the painstaking detective work. The OPERA team, to their credit, had spent months checking and rechecking their data before their bombshell announcement. They'd accounted for Earth's rotation, the curvature of the planet, even the subtle drift of continental plates. But science thrives on skepticism. Independent labs demanded replication. The Fermilab team in Chicago fired up their neutrino beam, while Japan's T2K experiment recalibrated their detectors. Meanwhile, internet sleuths dissected OPERA setup, zeroing in on a critical detail: the fiber optic cables that synchronized the experiment's atomic clocks. The truth, when it came, was equal parts embarrassing and enlightening. A loose cable connection had introduced a delay, making the neutrinos appear to arrive early. Another glitch, an improperly calibrated oscillator, compounded the error. What seemed like a revolution in physics was in fact a humble hardware hiccup. OPERA retracted their findings, but the episode left an indelible lesson. Science's greatest strength isn't infallibility, it's the self-correcting machinery of peer review. The OPERA team could have buried their doubts, but they chose transparency, inviting the world to scrutinize their work. That's how real progress happens. Not through grand proclamations, but through the messy, collaborative work of testing, failing, and refining. In the end, Einstein's relativity emerged unscathed, but the neutrino saga did more than preserve the status quo. It showcased science at its most honest. Every groundbreaking claim is met with a chorus of "prove it," and that's exactly how it should be, because sometimes the most valuable discoveries aren't about rewriting the laws of physics, but about reminding us how those laws withstand our best attempts to break them. The M-drive controversy reads like a modern-day physics rebellion, an engine that shouldn't work, yet somehow, in test after test, it seemed to. At first glance, the concept sounds straight out of science fiction, a tapered metal chamber dubbed the electromagnetic drive or M drive that allegedly generates thrust just by bouncing microwaves around inside. No propellant, no exhaust, just electricity converted into motion, defying Newton's third law that every action must have an equal and opposite reaction. When British engineer Roger Scheuer proposed it in the early 2000s, the scientific community scoffed. It was the perpetual motion machine of the space age, a fantasy. But then something unexpected happened. Independent teams, including a group at NASA Eagleworks lab, reported detecting tiny but measurable thrust. The numbers were minuscule. Some tests showed just a few micronewtons of force, barely enough to nudge a grain of sand. But in the vacuum of space, even that trace could add up over time, offering the dream of fuel-free propulsion. The implications were staggering. Imagine spacecraft that could cruise indefinitely without tanking up, slashing mission costs and opening the solar system like never before. But here's the catch: no one could explain how it worked. The microwaves bouncing inside the chamber had no obvious way to produce net thrust. Was it tapping into quantum fluctuations, warping space-time at a microscopic scale? Or was it all just experimental error, a mirage born from wishful thinking? Skeptics pounced. Critics argued that thermal expansion, the chamber heating unevenly during tests, could mimic thrust. Others pointed to Earth's magnetic field or even subtle vibrations in the lab equipment as potential culprits. Then came the kill shot. In 2021, a team at Dresden University built an ultra-sensitive torsion balance, isolating the M drive from every CONCEIV a BLE Chinese letter. Their result: no thrust, zero. The tiny forces earlier teams had seen likely came from external factors, not some revolutionary physics. Case closed, or so it seemed. But the M drive refuses to die quietly. Some researchers still argue that specific resonant frequencies or chamber geometries might unlock an elusive effect. Others suggest that if the drive were bending the rules of physics, it wouldn't fit neatly into existing models anyway. After all, history is littered with discoveries initially dismissed as impossible: X-rays, quantum entanglement, even the concept of black holes. Could the M drive be another outlier waiting for its Copernican moment? What makes this saga so compelling isn't just the science, it's the psychology. The M drive became a Rorschach test for how we confront anomalies. Do we dismiss them as noise or dare to question the framework itself? NASA ambiguous results paired with null findings from other labs leave the debate suspended in Schrödinger's cat-like limbo, neither fully alive nor entirely dead. For now, the M drive remains a cautionary tale about the line between breakthrough and blunder. But in a universe that constantly surprises us, it's also a reminder: sometimes the most impossible ideas are the ones worth testing, if only to discover why they're wrong. Saturn's North Pole holds one of the solar system's most mesmerizing mysteries, a colossal hexagon-shaped storm so precise it looks like it was etched by some cosmic draftsman. This six-sided vortex, wider than two Earths stacked side by side, has churned in perfect geometric harmony for at least 4 decades, maybe longer. While Earth's weather systems twist, merge, and vanish within days, Saturn's hexagon stands unshaken, a monument to nature's strangeness. The sheer scale of this phenomenon is staggering. Each side of the hexagon stretches nearly 9,000 miles, with winds screaming at over 200 miles per hour, faster than a Category 5 hurricane. Yet unlike Earth storms, which spiral chaotically, this one holds its crisp angles like a celestial honeycomb. When NASA Cassini probe first captured detailed images in 2006, scientists were floored. Atmospheric patterns simply don't behave this way, not on Earth. Not on Jupiter with its oval storms, not anywhere we've seen. Geometry this precise in a turbulent gas giant defies every textbook. So why a hexagon? Laboratory experiments offer clues. When fluids rotate rapidly in a circular tank, stable polygonal shapes can emerge: squares, triangles, even six-sided forms. It's as if Saturn's polar jet stream, a high-speed river of gas, hits just the right speed and viscosity to lock into this pattern. But here's the catch: no computer model can perfectly replicate it. Earth's most powerful simulations either produce messy, short-lived polygons or fail to match the hexagon's razor-sharp edges. Some theorists suggest Saturn's deep internal heat or unique atmospheric chemistry plays a role, while others wonder if the planet's layered winds, alternating bands moving east and west, act like invisible guides shepherding the storm into this unnatural symmetry. Then there's the eerie stability. Earth's polar vortices wobble, split, and reform with the seasons. Saturn's hexagon, it's a metronome. Voyager spotted it in the 1980s. Cassini watched it through 2017. Even as Saturn's northern hemisphere shifted from winter to summer, the hexagon persisted unbothered. This isn't just weather, it's a near-permanent tattoo on the planet's face. What really twists the knife is the hexagon's depth. Earth storms are skin-deep, fueled by sunlight and ocean heat. But Saturn's hexagon might plunge hundreds of miles into its atmosphere, a towering structure anchored by forces we can't yet measure. Recent studies hint that the planet's internal rotation, still not fully understood, could be pulling strings from below like a puppeteer orchestrating the chaos above. The hexagon stands as a humbling reminder. For all our rovers and telescopes, the solar system still guards secrets that laugh at our models. Maybe the answer lies in some exotic physics, or perhaps Saturn is just showing off. Either way, this six-sided enigma proves that nature's rulebook has pages we've yet to read, and some of the most stunning chapters are written in geometry. We think we've got the universe all figured out until we run the numbers and realize half its normal matter has gone missing. Not dark matter, not some exotic particle, but regular, run-of-the-mill protons and neutrons, the building blocks of everything we see. Astronomers call this the missing baryon problem, and it's one of those cosmic accounting errors where the math just won't balance. Here's the puzzle. When we tally up all the matter from stars, galaxies, and gas clouds, we're only accounting for about half of what the Big Bang's leftover glow tells us should be there. So where's the rest? The answer might be hiding in the loneliest places imaginable. The vast, almost empty voids between galaxies. Enter the warm, hot intergalactic medium, or WIM, a ghostly web of superheated gas so diffuse it's nearly invisible. Picture steam rising from a boiling pot, but instead of water molecules, it's a soup of ionized hydrogen and oxygen, stretched so thin that a single coffee mug's worth could fill a cubic light-year of space. This stuff is everywhere, threading the cosmic web like strands of spider silk, but it's been devilishly hard to spot. Why? Because it's too hot to absorb much light, yet too cool to glow brightly in X-rays. It exists in a Goldilocks zone of frustrating obscurity, just warm enough to slip through our nets, but not hot enough to wave a flag. For years, the WIM was just a hypothesis, a cosmic hiding place for the universe's lost matter. Then, in 2018, astronomers finally caught a glimpse. Using the Hubble Space Telescope, they detected the telltale fingerprints of highly ionized oxygen in the light of distant quasars' light that had passed through the WIM-tangled filaments on its billion-year journey to Earth. It was like finding smoke in a pitch-black room by shining a flashlight through it. The amounts were tiny, but when you scale it up, this faint signal could account for all the missing baryons woven into the fabric of space itself. But here's the twist: even with this breakthrough, the WIM remains maddeningly elusive. Mapping it fully would require next-gen telescopes capable of sensing ultra-faint X-rays like the planned Athena mission. And then there's the puzzle of why so much matter ended up here in these desolate corridors. Was it blown out by ancient supernova or slingshotted by colliding galaxies? Whatever the answer, the WIM isn't just a solution to a math problem, it's a reminder that the universe stashes its secrets in plain sight, hidden in the spaces we least expect. Some cosmic particles hit with so much energy, they make the Large Hadron Collider look like a toy. ultra-high-energy cosmic rays, subatomic bullets screaming through space, carry energies exceeding 100 million times anything our most powerful particle accelerators can produce. That's like a single proton packing the punch of a major league fastball. The crazy part, according to physics, these particles shouldn't exist. Their energy defies known limits, and their origins are a detective story spanning the cosmos. The first clue dropped in 1962, when scientists in New Mexico spotted a cosmic ray so energetic it was nicknamed the "Oh my God" particle. Since then, observatories like the Pierre Auger Array in Argentina have caught dozens more, each one a puzzle. Here's the dilemma: space is littered with cosmic microwave background radiation, the faint afterglow of the Big Bang, which should sap the energy of any ultra-high-energy particle over long distances. It's like running through a hail of bullets. Even the hardiest travelers shouldn't make it far. Yet these rays arrive with enough juice to suggest they came from relatively nearby. But when astronomers trace their paths backward, they often point to nothing. No supernova, no gamma-ray bursts, just empty void. So what's accelerating these particles to such impossible speeds? One suspect is active galactic nuclei, supermassive black holes at the hearts of galaxies, spinning jets of plasma at near light speed. These cosmic cannons could theoretically fire particles to extreme energies, but there's a catch. We'd expect to see more of them aligned with known black holes. Instead, the rays seem to arrive randomly, like snipers with no clear base. Then there's the beyond standard model camp, who argue these particles might be signatures of exotic physics, decaying super-heavy dark matter, defects in space-time itself, or even relics from extra dimensions. Imagine a microscopic crack in the universe's fabric, leaking energy we can't yet explain. The plot thickens with recent data suggesting some ultra-high-energy rays might be clustered, hinting at undiscovered sources lurking in our cosmic backyard. Others appear isotropic, evenly sprinkled across the sky, as if something omnipresent, like dark matter halos, is spraying them in all directions. It's a riddle wrapped in a paradox, particles too energetic to exist, arriving from places that shouldn't host them, pointing to physics we might not yet understand. Every new detection is both a clue and a taunt, reminding us that the universe still has aces up its sleeve. Until we catch one of these particles red-handed, or build detectors sensitive enough to trace them flawlessly, their origins will remain one of physics' most electrifying open cases. The cosmic microwave background is supposed to be the universe's fingerprint, a nearly uniform glow left over from the Big Bang that should look the same in every direction. But when scientists peered closer, they found something unsettling. Dubbed the axis of evil, this anomaly reveals an unexpected alignment between the CMB's temperature fluctuations and the plane of our solar system. It's as if the universe has a subtle but undeniable arrow pointing in one particular direction, violating a sacred cosmological principle that the cosmos should have no preferred orientation. The discovery sent shockwaves through the astrophysics community. The CMB's temperature variations are like tiny ripples frozen in time, reflecting the density fluctuations of the early universe. In a truly random cosmos, these ripples should be randomly scattered, no patterns, no hidden axes. Yet when researchers analyzed data from NASA Wilkinson Microwave Anisotropy Probe and later the Planck satellite, the statistics told a different story. The fluctuations weren't entirely chaotic. Instead, they seemed to align loosely with the ecliptic the path Earth and the planets trace around the Sun. It's as if the universe's oldest light is whispering a secret about our own backyard. Skeptics rush to explain it away. Could it be an artifact of the instruments, some subtle bias in how the data was collected? Planck's team ran exhaustive checks accounting for galactic dust, solar system emissions, even the spacecraft's own motion. The anomaly persisted. Others suggested it might be a statistical fluke, a cosmic mirage that would vanish with more precise measurements. But with each new dataset, the axis of evil stubbornly refused to disappear. The implications are profound. If this isn't an illusion, it challenges the cosmological principle, the bedrock assumption that the universe is homogeneous and isotropic on large scales. No matter where you stand, the cosmos should look broadly the same, no special places, no cosmic center. Yet here we are, with our solar system seemingly singled out by the universe's oldest light. Some theorists float radical alternatives. Could the early universe have been shaped by exotic physics, like primordial magnetic fields or defects in space-time? Others wonder if we're seeing the imprint of a multiverse, our bubble universe, brushing up against another in some higher dimensional form. Then there's the unsettling possibility that we're seeing evidence of a truly ancient influence. The solar system didn't exist when the CMB was emitted, so how could its orientation leave a mark, unless somehow the seeds of our planetary disk were sown in those first moments, with quantum fluctuations aligning in a way that would later shape everything from planet orbits to the CMB's patterns? It's a dizzying thought that the universe might have encoded our existence into its very first light. For now, the axis of evil remains one of cosmology's most tantalizing loose ends. It's a reminder that even our most cherished assumptions about the universe are provisional, subject to revision with each new discovery. Whether it's a clue to deeper physics or just a cosmic coincidence that's fooled us all, one thing's certain: the universe has a way of keeping us humble, revealing its mysteries only when it's good and ready. Galaxies aren't just scattered randomly across the cosmos, they're arranged in a web so vast it defies comprehension. Threads of galaxies, gas, and dark matter stretch billions of light years, forming walls and clusters that make up the universe's largest known structures. But when astronomers discovered the Hercules Corona Borealis Great Wall, they hit a problem. This colossal filament of galaxies spans an almost unimaginable 10 billion light-years, a structure so massive that according to our best models of cosmic inflation, it shouldn't exist at all. Think of the early universe like a balloon inflating faster than light itself. Cosmic inflation smoothed out irregularities, leaving behind only tiny density variations that later grew into galaxies and clusters. The math suggests there's a fundamental limit to how big any structure can be, about 1.2 billion light-years across. Beyond that scale, the universe should look roughly uniform no matter where you're standing. Yet the Great Wall laughs at that limit. It's not just a little too big, it's 8 times larger than theory allows, a cosmic behemoth that makes our local superclusters look like specks of dust. So how did it form? One possibility is that inflation wasn't as uniform as we thought. Maybe certain regions of the early universe expanded more slowly, allowing matter to clump together on scales that break the rules. Imagine blowing up a balloon with a few thicker patches. Those spots wouldn't stretch as smoothly as the rest, leaving behind dense knots. Another theory involves baryon acoustic oscillations, sound waves from the primordial universe that could have stacked galaxies in ways we don't fully understand. Or perhaps the Great Wall isn't a single structure at all, but a chance alignment of smaller filaments seen edge-on, like mistaking a pile of twigs for one giant log. But here's the kicker: the Great Wall isn't alone. There's the Sloan Great Wall, the South Pole Wall, and the Boss Great Wall, each one pushing the limits of what cosmic inflation should allow. Some researchers argue these might just be statistical flukes, cosmic wrinkles that only appear connected because of our limited vantage point. After all, we're seeing these structures in 2 dimensions, like trying to map a forest by looking at shadows on a wall. Yet, even accounting for perspective, their sheer scale keeps physicists up at night. The implications are staggering. If these walls are real, they might force us to rewrite our understanding of inflation, or even consider entirely new physics. Could the universe have experienced multiple inflationary phases, each leaving behind its own fingerprint? Are we seeing the scars of collisions with other bubble universes in a multiverse? Or is there some exotic force, long since faded, that sculpted these titanic structures before disappearing into the cosmic background? For now, the Hercules Corona Borealis Great Wall stands as both a monument and a provocation. It's a reminder that the universe operates on scales we're only beginning to grasp, and that even our most elegant theories might just be rough sketches of a far stranger reality. Every time we think we've mapped the cosmos, it shows us another layer, another mystery, another wall we'll have to climb to see what's on the other side. The universe is unimaginably vast, with billions of galaxies, each hosting billions of stars. So why does it feel so empty? This is the Fermi paradox, the glaring contradiction between the high probability of alien civilizations existing and the eerie silence we encounter when we listen for them. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox forces us to confront an unsettling possibility. Despite the math saying we should have neighbors, something must be stopping us from finding them. One of the most chilling explanations is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication, the terrifying part. We don't know if we've already passed it or if it's still ahead of us. If the filter is behind us, say, the near-miraculous jump from simple chemistry to self-replicating life, then we might be among the rare few who made it. But if it's ahead, like self-destruction through nuclear war or climate collapse, then every civilization that reaches our level might be doomed to flicker out before making contact. It's a cosmic game of Russian roulette, and we have no idea how many chambers are loaded. Then there's the zoo hypothesis, which suggests advanced civilizations know we're here but choose not to interfere, treating Earth like a nature preserve. Picture ants in an ant farm, unaware they're being observed by giants with motives beyond their comprehension. This idea plays into our fear of being insignificant. What if we're just a curiosity in some alien biologist's notebook? Others propose the dark forest theory, a grim take where civilizations stay silent because broadcasting your location invites destruction. In this scenario, the universe is full of predators, and every species learns to hide or perish. But not all solutions are so bleak. Maybe we're simply too early. The universe is 13.8 billion years old, but complex life might only be possible now, after countless stars forged the heavy elements needed for planets and biology. Alternatively, we could be looking for the wrong signals. Our radio telescopes are primitive compared to what an advanced species might use, like trying to spot a smoke signal in a world that's moved on to fiber optics. The paradox lingers because every answer raises new questions. Are we alone because life is vanishingly rare, or because intelligence is a dead end? Are we being watched, ignored, or is the universe far stranger than we've dared to imagine? Until we find proof, whether it's a signal, an artifact, or the chilling realization that we've already hit the filter, the Fermi paradox remains the universe's most haunting riddle, a mirror reflecting our deepest hopes and fears about our place in the cosmos. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their event horizon, then white holes are their rebellious twins, cosmic fire hydrants blasting matter outward with unstoppable force. These hypothetical objects, first dreamed up as mathematical curiosities in Einstein's equations, are the exact inverse of their dark counterparts. Where a black hole's gravity is so intense nothing escapes, a white hole would repel all matter, refusing to let anything in. Picture a one-way door where space-time itself vomits up light, gas, and perhaps even entire galaxies in a violent, never-ending eruption. Theoretically, if you could stand at the edge of a white hole, you'd witness the Big Bang in miniature, a single point disgorging the building blocks of reality at speeds approaching infinity. But here's the catch: despite decades of searching, no one has ever spotted one. Not a single confirmed white hole exists in our observable universe. So why do physicists keep talking about them? The answer lies in the tangled web of quantum gravity. In loop quantum gravity, a leading theory attempting to marry Einstein's relativity with quantum mechanics, black holes might transform into white holes at the end of their lives. Imagine a black hole evaporating via Hawking radiation until it hits a critical point. Instead of vanishing, it could rebound like a compressed spring, exploding outward as a white hole in a process taking billions of years. This cosmic metamorphosis would preserve information, sidestepping the black hole information paradox while offering a spectacular, if hypothetical, finale to a black hole's life cycle. Another wild possibility: white holes could be the secret source of dark matter. Some theorists suggest these objects might have formed in the early universe's chaos, ejecting streams of exotic particles that now weave invisibly through space. Others speculate that white holes could explain fast radio bursts, those mysterious, high-energy cosmic flashes with no clear origin. If a white hole burped out a concentrated jet of plasma, it might look exactly like the bizarre signals puzzling astronomers today. Yet the absence of observational evidence keeps white holes squarely in the realm of theory. Some argue they're mathematical ghosts, artifacts of equations that don't reflect physical reality. After all, the second law of thermodynamics says entropy always increases, and a white hole spontaneously spewing order into the universe seems to defy that rule. But then again, so did black holes before we found them. The universe has a habit of taking impossible ideas and throwing them in our faces. Whether white holes remain a thought experiment or someday reveal themselves as cosmic reality, one thing's certain: they're a thrilling reminder that even the most outlandish predictions can reshape our understanding of space, time, and the laws that govern them. Stretching over an almost incomprehensible billion light-years, the Eridanus supervoid is one of the most baffling structures ever discovered in our universe. A yawning emptiness so vast it's left scientists debating whether they're staring at a cosmic mirage or something far stranger. This colossal void isn't just an absence of galaxies. It's a freezing anomaly in the cosmic microwave background, the afterglow of the Big Bang. Dubbed the cold spot, this region of space is noticeably chillier than its surroundings, as if the universe left a freezer door open in one corner of the cosmos. The question is, what could possibly carve such a titanic hole in the fabric of reality? At first glance, the explanation seems straightforward. Void's massive, galaxy-poor regions are common in the universe's web-like structure. But the Eridanus supervoid isn't just big. It's unusually big, stretching the limits of what cosmologists thought possible under standard inflationary models. If this were just an empty bubble, its sheer scale should have made it statistically improbable, like rolling a die 100 times and getting nothing but sixes. Yet there it sits, a cosmic blind spot that defies expectations. The cold spot's temperature dip aligns eerily with the void's location, suggesting a connection. When light from the CMB passes through such a void, it loses energy climbing out of the gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. In theory, that could explain the chill, except the energy drop observed here is far steeper than the void alone should produce. That discrepancy has fueled wilder theories. Some researchers propose the cold spot might be the fingerprint of a cosmic defect, a scar from the universe's violent infancy. Imagine space itself tearing slightly during rapid expansion, leaving behind a wrinkle that cooled the light passing through it. Others wonder if we're seeing evidence of a collision with another universe, a bubble from the multiverse brushing against our own and leaving behind a bruise in the CMB. It's a tantalizing thought, the cold spot as a window into realities beyond our own, a place where the rules of physics might be radically different. Skeptics, however, aren't ready to rewrite cosmology just yet. They argue the cold spot and the supervoid might not be directly linked, a case of two rare phenomena overlapping by chance. Advanced simulations suggest that even in a universe governed by known physics, such outliers can emerge purely through random fluctuations. It's like shuffling a deck of cards and accidentally dealing a perfect suit, unlikely but not impossible. Then there's the measurement problem. Mapping something a billion light-years across is no easy feat, and some astronomers contend the void's size might be overestimated, its edges blurred by incomplete data. What makes this debate so electrifying is the stakes. If the Eridanus supervoid and its cold spot are truly connected, it could mean our universe has textures we've never imagined, ancient imperfections, or even portals to other dimensions. If they're not, it forces us to ask how well we really understand the cosmic microwave background, the very blueprint of creation. Future telescopes, like the European Space Agency's Euclid mission, might finally settle the argument by mapping the void's true shape and the cold spot's boundaries with unprecedented precision. Until then, this billion light-year enigma remains a humbling reminder. Even the emptiest corners of space might hold the keys to the universe's deepest secrets. Imagine a cosmic game of hide and seek where the hider makes up 85% of the players, yet leaves no footprints, casts no shadow, and never breathes a sound. That's dark matter in a nutshell, the universe's ultimate ghost, silently sculpting galaxies and bending light with its gravitational pull while remaining utterly invisible to every telescope we've ever built. We know it's there because galaxies spin faster than they should, clusters glow with distorted light from unseen mass, and the cosmic web's grand structure couldn't exist without it. But what is it? The answer might rewrite physics itself. For decades, the leading candidates were WIMP, weakly interacting massive particles. Picture a swarm of subatomic phantoms, each heavier than a proton but so aloof they barely notice normal matter exists. These hypothetical particles emerged as dark matter's golden child because they fit neatly into supersymmetry, a theory that elegantly pairs every known particle with a heavier twin. Detecting them should be possible. If a WIMP ever grazed an atom in an ultra-sensitive underground detector, it might trigger a tiny flash of light or vibration. Yet after decades of hunting with instruments buried miles beneath mountains to block cosmic noise, the scoreboard remains empty, not a single confirmed WIMP signal. Some researchers argue we've been looking for the wrong mass range, while others whisper that maybe, just maybe, we've been chasing a beautiful idea that doesn't exist. Enter Action's dark matter's quirky underdog. 1 trillion times lighter than electrons, these hypothetical particles were dreamed up to solve an unrelated puzzle in quantum physics. Unlike WIMP, Actions wouldn't bump into atoms, they'd transform into photons in the presence of strong magnetic fields. Experiments like the Action Dark Matter experiment ADMS use powerful magnets and ultra-cold cavities to coax these shy particles into revealing themselves. It's like tuning a cosmic radio, searching for one faint note in a symphony of static. While no action has been caught yet, their theoretical elegance keeps hope alive. If they exist, they could be everywhere, a fine mist of quantum fluff drifting through your fingertips right now, oblivious to everything but gravity. Then there's the radical alternative. What if dark matter isn't a particle at all? Modified Newtonian dynamics, or MUND, suggests gravity behaves differently on galactic scales than Einstein predicted. Instead of invoking unseen matter, MUND tweaks the math so that stars at a galaxy's edge orbit faster without needing extra mass. It's a bold move, throwing out the cosmic placeholder and rewriting the rules instead. But MUND faces its own hurdles. While it explains some galaxy rotations beautifully, it stumbles when applied to colliding galaxy clusters like the Bullet Cluster, where visible matter and gravitational pull clearly separate, like a car's skeleton and its shadow parting ways in a crash. For many scientists, that's a deal-breaker. The truth is, each theory has its own Achilles heel. WIMP missing in action, actions still hypothetical. MUND incomplete. Some theorists are now exploring even wilder ideas. Primordial black holes forged in the Big Bang's first seconds, or sterile neutrinos that oscillate into dimensions we can't see. Others wonder if dark matter interacts with itself through some unknown force, creating intricate substructures we've yet to map. What makes this search so electrifying isn't just the mystery, it's the stakes. Dark matter isn't some distant curiosity. It's the scaffolding of reality, the hidden hand that shaped every galaxy, including our own. Crack its code, and we might unlock secrets about the universe's birth, evolution, and ultimate fate. Until then, we're left with a humbling truth. Most of the cosmos is made of something we can't see, can't touch, and don't understand. It's as if we've been reading a novel where every other word is written in ink only the universe can see, and we're just beginning to guess at the story. When NASA Curiosity rover first sniffed methane in Mars' thin air back in 2013, the scientific community held its breath. Here was a gas that, on Earth, is almost synonymous with life belched by cows, seeping from swamps, a byproduct of biological activity. Yet on the red planet, with its barren, radiation-scorched surface, the presence of methane flickering in and out of detection wasn't just surprising, it was downright paradoxical. The readings weren't consistent either. Some days, methane levels spiked to 10 times the background average. Other times, the gas vanished entirely, as if Mars itself was playing a cosmic game of hide and seek. What makes methane so intriguing is its fragility. Solar radiation and chemical reactions in Mars' atmosphere should break it down within a few hundred years, meaning any methane we detect today can't be some ancient relic. It's being replenished actively or intermittently by something. The question is, what? One camp points to geology. Mars is home to volcanic regions like Olympus Mons, though no active eruptions have been observed. Could residual geothermal heat be cooking methane out of mineral deposits deep underground? Certain rock formations, like olivine, can produce methane when exposed to water and heat through a process called serpentinization. If Mars has hidden hydrothermal systems, they might be quietly feeding this enigmatic gas into the atmosphere. But then there's the elephant in the room: biology. On Earth, the vast majority of methane comes from living organisms, from microbes in wetlands to the digestive tracts of termites. If life ever took hold on Mars, perhaps in subsurface aquifers shielded from the deadly surface radiation, it's not impossible that Martian microbes could be producing methane as a metabolic byproduct. Imagine extremophile organisms eking out an existence in briny pockets beneath the soil, their faint biochemical whispers drifting up through cracks and pores to tease our instruments. The idea isn't far-fetched. We've found life thriving in Earth's most inhospitable corners, from acidic hot springs to Antarctic ice sheets. The plot thickens with orbital data. Europe's Trace Gas Orbiter, designed specifically to study Mars' atmospheric chemistry, has largely failed to confirm Curiosity's methane spikes. This inconsistency could mean the gas is localized, dissipating quickly near the surface, or that it's being released in brief, episodic bursts like a pressurized underground reservoir, occasionally venting through weak spots. Alternatively, it might hint at a measurement discrepancy between ground-based and orbital instruments. Perhaps the most tantalizing clue comes from the seasonal patterns in Curiosity's data. Methane levels appear to rise during Mars' warmer months and drop in winter, suggesting a process tied to temperature. Could it be that heat is triggering the release of trapped gas from icy clathrates, cage-like structures in the soil that trap methane molecules, or stimulating microbial activity in transient liquid water films? Until we drill deeper or return samples to Earth, the Mars methane mystery will linger, a riddle wrapped in red dust. Every new detection and every confounding non-detection adds another piece to a puzzle that might rewrite our understanding of Mars' hidden vitality. Whether the answer points to geology, biology, or something even stranger, one thing's clear: the red planet still has secrets to spill, and methane is its most tantalizing clue yet. Our galaxy isn't just drifting aimlessly through space, it's sprinting towards something massive, invisible, and utterly mysterious. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's yanking the Milky Way and thousands of other galaxies toward it at a staggering 14 million miles per hour. But here's the catch: we can't see it. This cosmic heavyweight lurks behind a thick curtain of stars, dust, and gas in the Milky Way's disk, a region so obscured we call it the zone of avoidance. It's like trying to spot a mountain through a blizzard, all while hurtling toward it at breakneck speed. The prime suspect, the Norma cluster, a dense gathering of galaxies about 250 million light-years away, sitting near the heart of this gravitational tug-of-war. Packed with massive ellipticals and swirling spirals, Norma's combined gravity might explain part of the pull, but there's a problem. Even this colossal cluster isn't nearly massive enough to account for the full force of the Great Attractor. It's as if we've found a footprint, but the beast itself is still hiding in the shadows. Some researchers speculate that an even larger structure lies beyond Norma, perhaps a supercluster we've yet to map, its mass warping space-time like a hidden boulder bending a river's current. Mapping this region is like navigating a maze blindfolded. The zone of avoidance isn't just a minor inconvenience, it's a galactic blind spot where the Milky Way's own bulk blocks our view. Optical telescopes see nothing but a wall of cosmic fog. To pierce through, astronomers have turned to infrared and radio wavelengths, which cut through the dust like night vision goggles. Slowly, painstakingly, they've charted hidden galaxies lurking in the void, each one adding weight to the Great Attractor's gravitational grip. Yet the deeper we look, the stranger it gets. Recent surveys suggest the Great Attractor might just be a waypoint in an even grander journey. Beyond it lies the Shapley supercluster, the most massive concentration of galaxies in our cosmic neighborhood. Some argue Shapley's gravity is the real puppet master, with the Great Attractor acting as a middleman in this celestial game of tug-of-war. Others wonder if we're seeing the fingerprints of dark matter on an unprecedented scale, an invisible scaffold guiding the universe's largest structures into place. The irony is delicious. Here we are, racing toward a mystery we can't fully see, tugged by forces we don't fully understand. Whether it's Norma, Shapley, or something even stranger, the Great Attractor reminds us that the universe is always in motion, always hiding its grandest designs just out of sight. Every new observation peels back another layer, revealing not just answers but deeper questions about the hidden architecture of the cosmos. And one thing's certain: until we solve this gravitational riddle, we're all just passengers on a galactic bullet train hurtling toward the unknown. Einstein's theory of relativity isn't just some abstract cosmic rulebook, it's hard at work in your phone's GPS, correcting for time itself bending around our planet. Here's how it should work. Atomic clocks aboard satellites tick ever so slightly faster than their Earth-bound counterparts because they're higher in Earth's gravitational well, where space-time isn't stretched as tight. Relativity predicts this precisely without adjusting for this time warp. Your navigation would drift off by about 6 miles a day, but in the past decade, something peculiar emerged. When physicists compared the ticking rates of ultra-precise atomic clocks in orbit with those on the ground, they found tiny discrepancies. Relativity's equations were almost perfect, but not quite. The clocks weren't just drifting due to gravity and velocity, they were straying in ways Einstein's math couldn't fully explain. These anomalies are vanishingly small, we're talking billionths of a second per year. But in the hypersensitive world of quantum timekeeping, even a whisper of inconsistency raises eyebrows. One leading theory points to the limits of relativity itself. Einstein's equations beautifully describe gravity's pull on planets and stars, but they don't play well with quantum mechanics, the rules governing the subatomic realm. Atomic clocks rely on the vibrations of atoms like cesium or rubidium, which are fundamentally quantum objects. Could their tiny discrepancies be a clue that gravity operates differently on quantum scales? Some researchers think so, proposing that an unseen quantum gravitational effect, perhaps space-time itself pixelating at microscopic levels might be nudging these clocks off kilter. Then there's the dark matter angle. What if invisible halos of this enigmatic substance are subtly warping space-time around these satellites in ways we haven't accounted for? Or could Earth's rotation be dragging space-time along with it like molasses, creating faint ripples that tweak the clock's rhythms? The truth is, every explanation feels like grasping at cosmic straws. The anomalies are too small to fit neatly into any existing theory, yet too persistent to ignore. That's where quantum gravity steps in, the holy grail of modern physics. Theories like loop quantum gravity or string theory attempt to bridge relativity and quantum mechanics, suggesting that space-time isn't smooth but granular, woven from tiny loops or vibrating strings. If true, these building blocks might interact with atomic clocks in unexpected ways, introducing minuscule timing hiccups. Imagine trying to measure the flow of a river with a stopwatch, unaware that the water is actually made of trillions of tiny droplets, each one tweaking the current just a little. The stakes are higher than just fixing GPS drift. If these clock discrepancies hold up under even sharper scrutiny, they could crack open a window into physics beyond Einstein, revealing a universe where gravity and quantum weirdness finally shake hands. Future experiments like placing atomic clocks on the International Space Station or even in deeper space might finally tease apart these effects from cosmic noise. Until then, those whispering clocks serve as a reminder. Even our most trusted laws of physics might have uncharted fine print, waiting to be decoded one tick at a time. The Big Bang wasn't just an explosion, it was a cosmic alchemy lab forging the universe's first elements in a fireball of unimaginable heat. Hydrogen, helium, and a smattering of lithium were cooked up in those first frenetic minutes, their abundances calculated with exquisite precision by modern physics. Yet when astronomers peer into the oldest stars, the ones that formed from this primordial soup, they find a glaring discrepancy. The lithium-7 levels are off by a factor of 3. It's as if the universe's recipe book has a missing page, and scientists are scrambling to figure out whether the stars ate the ingredients or the laws of physics need rewriting. One camp blames stellar culprits. Ancient stars, those celestial time capsules, might have destroyed lithium over billions of years through processes we've yet to fully grasp. Picture a star's core as a turbulent factory where lighter elements fuse into heavier ones. Under normal conditions, lithium burns up quickly in these nuclear furnaces, but some stars have deep convection currents that could drag lithium down to their cores like cosmic conveyor belts where it's annihilated. Others propose that cosmic rays, those high-energy particles zipping through space, might smash into atoms in stellar atmospheres, breaking lithium apart like a wrecking ball hitting stained glass. If either of these mechanisms is more efficient than we've modeled, it could explain the shortfall. But then there's the nuclear option, literally. What if the Big Bang's lithium yield wasn't what we've calculated? The predictions hinge on our understanding of particle physics, particularly the rates of nuclear reactions in the early universe's extreme conditions. Tweaking those numbers by just a few percent could resolve the mismatch, but it risks opening Pandora's box. Maybe unknown particles influenced these reactions, or perhaps the universe's expansion rate in those first moments wasn't as uniform as we assume. Some theorists even speculate about exotic physics, like variations in the fundamental constants governing nuclear forces. A heresy to conventional models, but a tantalizing fix for the lithium problem. The stakes are higher than just accounting for a few missing atoms. Lithium is a key piece of the puzzle connecting particle physics to cosmology, a bridge between the infinitesimally small and the astronomically vast. If stars are destroying it more efficiently than thought, we'd need to revise how we interpret the chemical fingerprints of the earliest galaxies. If the fault lies with the Big Bang's math, it could hint at physics beyond the standard model, new particles, forces, or even dimensions that left their mark on the universe's first 3 minutes. For now, the mystery endures, a quiet rebellion in the data that refuses to be ignored. Every new observation of ancient stars, every refined nuclear cross-section in lab experiments brings us closer to an answer. Whether the culprit turns out to be stellar dynamics, cosmic rays, or a fundamental rewrite of physics, one thing's certain: the universe's missing lithium is more than a cosmic accounting error. It's a whisper from the dawn of time, reminding us that even our best theories might still be missing a few ingredients. Venus is a world of contradictions, a planet so similar to Earth in size and composition, yet so alien in its behavior. While its surface crawls at a snail's pace, taking 243 Earth days to complete a single rotation, its atmosphere races around the planet at over 200 miles per hour, completing a full circuit every 4 days. This phenomenon, known as superrotation, defies everything we know about planetary weather systems. On Earth, our atmosphere is mostly dragged along by the planet's rotation, with winds and storms creating localized turbulence but never outpacing the ground below. Venus, however, operates on a different set of rules, leaving scientists scratching their heads over how its atmosphere gathers enough momentum to become a runaway carousel of gas. The mechanics of this high-speed atmospheric dance are anything but intuitive. Imagine trying to stir a cup of coffee where the liquid spins 60 times faster than the cup itself. It shouldn't be possible without some hidden force doing the stirring. One leading theory points to thermal tides, where the sun's blistering heat on Venus's day side creates extreme pressure differences, driving massive waves in the atmosphere. These waves could transfer energy from the planet's sluggish surface to its upper layers, like a cosmic conveyor belt accelerating the winds. Another clue lies in Venus's thick sulfuric acid clouds, which absorb sunlight and irradiate it as heat, potentially fueling a self-sustaining cycle of motion. But here's the catch: computer models struggle to replicate the observed wind speeds without introducing fictional forces. The math just doesn't add up yet. Then there's the mystery of momentum transfer. On Earth, friction between the atmosphere and the ground helps keep our weather systems in check. Venus's surface, though scorching and inhospitable, should still exert enough drag to slow those hurricane-force winds over time. So why doesn't it? Some researchers speculate that planetary-scale turbulence, think Jupiter's great red spot but spanning the entire globe, acts like a giant flywheel, storing and redistributing angular momentum in ways we don't yet understand. Others wonder if Venus's lack of oceans plays a role. Earth's seas absorb and release heat slowly, stabilizing atmospheric circulation. Venus, with its bone-dry surface, might lack these natural breaks, allowing its winds to spiral out of control. The stakes aren't just academic. Unraveling superrotation could shed light on exoplanets with similar extremes, helping us identify which ones might host stable climates or bizarre weather systems of their own. Missions like Japan's Akatsuki orbiter, which watches Venus's atmosphere in infrared, are slowly piecing together the puzzle. But for now, the planet remains a whirlwind of unanswered questions, a reminder that even in our own cosmic backyard, nature still has a few tricks up its sleeve. Whether it's hidden waves, chaotic turbulence, or something even stranger, Venus's superrotation stands as one of the solar system's most mesmerizing enigmas, a tempest in a celestial teapot we're only beginning to understand. Just beyond Neptune's orbit, where sunlight is 1,000 times dimmer than on Earth, the Kuiper belt should be teeming with icy leftovers from the solar system's birth, but astronomers have stumbled upon something bizarre. Around 50 astronomical units from the Sun, this frozen junkyard of comets and dwarf planets suddenly drops off, as if someone drew a cosmic boundary line. This abrupt vanishing act, known as the Kuiper Cliff, defies every model of how planetary systems form. If the Kuiper Belt were a city, it wouldn't fade gradually into suburbs, it would end at a sheer wall with nothing but emptiness beyond. The most tantalizing explanation, an unseen world lurking in the darkness, Planet 9, a hypothetical giant up to 10 times Earth's mass, could be shepherding the Kuiper Belt's outer edge with its gravity, either hurling objects inward or flinging them into deep space. Picture a hidden bull in a cosmic china shop, its gravitational kicks clearing a path through the debris. Computer simulations show such a planet could explain not just the Kuiper Cliff, but also the peculiar, clustered orbits of some extreme trans-Neptunian objects, which tilt and loop like they're dancing to an invisible piper's tune. Yet after years of scanning the skies, Planet 9 remains elusive. Is it a stealthy behemoth camouflaged by distance, or are we chasing a phantom? Then there's the observational bias argument. Could the Kuiper Cliff simply be an illusion, a gap in our telescope's reach? Beyond 50O, objects grow fainter and slower moving, slipping through surveys like sand through a sieve. The New Horizons probe, which flew past Pluto in 2015, offered a reality check. Its extended mission found a handful of distant Kuiper Belt objects, but nowhere near enough to fill the void. If there's a hidden population out there, it's playing an expert game of hide and seek. But here's where it gets weirder. Even if Planet 9 exists, some calculations suggest its gravity alone couldn't sculpt the Kuiper Cliff so sharply. That's led to wilder theories. Maybe the young sun stole icy bodies from a passing star in its birth cluster, depositing them in a truncated disk. Or perhaps the cliff marks the outer edge of the solar system's primordial pebble cloud, the original building blocks of planets which never fully coalesced beyond this boundary. Each hypothesis feels like a piece of a jigsaw puzzle from different boxes close enough to tease, but never quite snapping into place. The Kuiper Cliff isn't just a curiosity, it's a forensic clue to the solar system's untold history. Whether the culprit turns out to be a hidden planet, a long-vanished stellar intruder, or something even stranger, this frozen frontier proves one thing: our cosmic neighborhood still has secrets buried in the ice, waiting for the next intrepid explorer to dig them up. The Black Knight satellite has haunted conspiracy theories for decades, a shadowy, alien spacecraft supposedly orbiting Earth for thousands of years, watching us in silence. Stories claim it broadcasts mysterious signals, that ancient civilizations knew of its presence, even that NASA has covered up its existence. But peel back the layers, and you'll find a fascinating case study in how myths evolve from mundane beginnings into cosmic legends. It all started in 1954 when newspapers reported that a retired Marine Corps pilot named Donald Kehoe claimed the U.S. government had detected 2 satellites orbiting Earth, impossible at the time since no country had launched one yet. The story spiraled from there. By the 1960s, radio enthusiasts were picking up odd signals they couldn't explain, and soon whispers spread that an extraterrestrial probe was circling our planet. The legend grew teeth when, in 1998, a tangle of debris photographed during a space shuttle mission was misidentified as the Black Knight, a dark, jagged object floating ominously against the blue curve of Earth. But here's where reality steps in. That infamous photo, it was a thermal blanket lost during an earlier spacewalk, nothing more. The so-called alien signals. Natural radio emissions or human-made interference misread through the lens of excitement. Even the original Kehoe story unravels under scrutiny. No evidence supports his claim of secret satellites, and astronomers at the time confirmed no such objects existed. Yet the myth persists, fueled by a mix of misinterpretation and pop culture. A Norwegian scientific satellite launched in the 1960s with its looping polar orbit was occasionally visible under peculiar lighting conditions, mistaken by observers for something far more sinister. Online forums amplified the mystery, stitching together grainy photos, outdated news clippings, and half-truths into a compelling but entirely fictional narrative. What makes the Black Knight legend so enduring isn't just our fascination with the unknown, it's the way it reflects our desire for mystery. In a universe that often feels explainable, the idea of an ancient alien sentinel watching from the void is irresistible. But science offers its own kind of poetry. The truth about space debris, thermal blankets, and misidentified satellites is a reminder of how easily reality can be reshaped by imagination. The real Black Knight isn't lurking in orbit, it's the human mind's uncanny ability to turn the ordinary into the extraordinary. So next time you hear about this phantom satellite, remember, sometimes the most intriguing space mysteries aren't found in the stars, but in the stories we tell about them. And that, in its own way, is just as fascinating as any alien artifact could ever be. Imagine floating in the endless void of space, utterly alone, when suddenly consciousness flickers to life. Not in a body, not on a planet, but as a lone, self-aware brain conjured from random quantum fluctuations. This is the Boltzmann brain paradox, one of the most unsettling thought experiments in cosmology, a scenario where the laws of probability twist reality into something unrecognizable. Named after the 19th century physicist Ludwig Boltzmann, who grappled with the nature of time and entropy, the paradox forces us to confront a bizarre implication of our universe's lifespan. Given enough time, even the most unlikely events become inevitable. And that includes the spontaneous formation of a fully formed, thinking mind in the middle of nothingness. The crux of the paradox lies in entropy, the measure of disorder in a system. Boltzmann realized that our universe's arrow of time, the reason we remember the past but not the future, is tied to entropy's relentless increase. But here's the twist: in an infinite or near-infinite universe, entropy doesn't always move in one direction. Given enough time and space, particles bouncing around at random will occasionally arrange themselves into low-entropy states, like a shattered vase reassembling itself. Most of these fluctuations are mundane, a patch of order here, a brief symmetry there, but statistically, given eternity, even something as complex as a functioning human brain could materialize out of chaos, complete with fabricated memories of a life that never was. This leads to a chilling conclusion: if Boltzmann brains are possible, they're inevitable. In fact, in an infinitely old or infinitely large universe, they'd vastly outnumber ordinary, biologically evolved minds like ours. So why does reality feel so stable and ordered? Why don't we find ourselves as lonely brains drifting in the void? That's the paradox. If the math says Boltzmann brains should dominate, then the very fact that we aren't one becomes a cosmic anomaly. Some theorists argue this undermines our trust in reality itself, turning existence into a hall of mirrors where we can't be sure we're not just fleeting fluctuations. The implications ripple into debates about the multiverse. If our universe is just one bubble in an infinite cosmic foam, do other universes have different entropic rules that make Boltzmann brains more or less likely? Could certain physical constants like the strength of dark energy be fine-tuned precisely to avoid a reality where disembodied minds outnumber stars? Others propose that the paradox is a red flag signaling flaws in our understanding of quantum mechanics or cosmology. Maybe the universe isn't infinite after all, or perhaps consciousness requires more than just the right arrangement of atoms, a soul, a substrate, something beyond pure physics. Yet for all its existential dread, the Boltzmann brain paradox isn't just a philosopher's puzzle. It's a stress test for our models of reality, pushing them to the breaking point to see where they crack. Whether the answer lies in new physics, a deeper grasp of entropy, or a radical rethinking of time itself, one thing's clear: the universe is stranger than we can imagine, and our place in it might be far more precarious or miraculous than we've dared to believe. From the eerie whispers of the Wow signal to the defiant geometry of Saturn's hexagon, from the phantom tug of dark energy to the quantum riddles of black holes, these 30 cosmic enigmas aren't just gaps in our understanding, they're the jagged edges where science meets the unknown. Each one is a testament to the universe's flair for chaos, a reminder that no matter how many equations we scribble or telescopes we launch, space remains the ultimate rebel, rewriting the rules as we scramble to keep up. Think about it, we've mapped the human genome, split the atom, and touched the dusty face of Mars, yet the cosmos still drops clues like a mischievous trickster, neutrinos that almost break light speed, galaxies moving faster than gravity allows, stars that flicker like malfunctioning streetlights. These aren't just puzzles, they're invitations. Every anomaly, every contradiction is a crack in reality's facade, hinting at forces and dimensions we've yet to name. What makes these mysteries so thrilling isn't just their defiance of science, it's their promise. Their proof that exploration didn't end with the Apollo program or the Hubble Deep Field. The next great discovery might be lurking in the next dataset, the next lab experiment, the next flash of radio static from the void. Maybe you'll be the one to crack the Fermi paradox or spot the glitch in relativity that explains those atomic clock hiccups. The universe isn't just full of secrets, it's waiting for you to uncover them. So stay curious, keep looking up, and if you crave more mind-bending journeys to the edges of physics, don't forget to subscribe, because the cosmos isn't done surprising us, and neither are we. The next mystery is just a click away.